maximum value, the capacitor is fully charged at its plates. Switch is open, no current is flowing. So after attaining to the maximum charge value, we have kept this switch as an open. Then, so what will happen? The condenser will be discharging. How it will be discharging? It will be discharging once the switch is closed and there is no EMF in the circuit. You can see that there is no EMF in the circuit. We have removed the EMF and we have closed the switch as then the current is flowing in this particular direction, and we can say that the capacitor is discharged. So capacitor is fully discharged, and once we say that the condenser is fully discharged, will there be any current in the circuit? No. So there won't be any current if the capacitor is fully discharged. So if we take this circuit and according to the Kirchhoff's voltage law or loop law or second law, it will be minus Q by C minus IR should be equal to 0, isn't it? Minus Q by C minus IR is equal to 0. We will do this I nothing but as a dQ by dt. So minus dQ minus d by minus Q by C minus R into dQ by dt is equal to 0. This one, okay. And then after mathematical expressions and all, so we can get it as Q is equal to capital Q into exponential of minus t by CR. So here the boundary conditions will be when time t is equal to 0, the charge on the condenser was fully charged. So the Q will be equal to Q naught or Q will be equal to CE. So after substituting the boundary condition, we will get as Q is equal to Q naught or capital Q into exponential of minus t by CR. And this is in the form of current. The current in the circuit will be minus Q by CR into exponential of minus t by CR. So we can say the charge in the capacitor decreases with time. Current is also decreasing with respect to time. This is the discharging. So we have an equation. If you derivate it with respect to time, so dq by dt, you will get it as q naught into exponential of minus t by CR. So here you can see both for the current as well as the charges. So here when we say that minus t is equal to RC, this will come like exponential of minus 1 or 1 by E as is equal to value of 2.718, you will get it as 0.37. So we can say that the current attains to, or the charge discharges to 37% of its maximum charge when the tau or time constant is equal to RC seconds. And this is related to current and this is related to charge value. So if you see the summary, charging as well as discharging, when the condenser was charging, when the circuit or when the switch was closed, then the charge on the condenser in the circuit should be equal to a maximum charge Q naught or Q into 1 minus exponential of minus t by CR. Whereas when we allowed the condenser to discharge after removing the EMF in the circuit, then the charge on the condenser was equal to small q was equal to capital Q or maximum charge into exponential of minus t by RC. Now let us understand LC circuit. Now we have seen the role of R in the circuit, L as well as condenser in the circuit. So now let us have the combination called L and C. inductance and condenser. So when switch S is closed, no current in the circuit, or there will be no charge in the condenser. So what will happen when the switch S is closed? This plate is charged with plus and this is with a minus. This is we can say that the minus Q and this is a plus Q, and at time t is equal to 0 we can say here as in I is equal to 0. Okay, this is the first one, and here at a time t is equal to quarter t by 4 the charge will be 0, whereas we can see that there is a magnetic field generated across this particular condenser. So here I can say earlier as an electric field, now a magnetic field. Again an electric field is generated, but the direction is reversed. Okay, okay. When t is equal to capital T by 2. Then again, if you take as in t is equal to 3 by 4th of capital T, then there is a magnetic field where I say the charge on the condenser is 0. So if you have observed, there will be an electric field and then again a magnetic field. Again an electric field and again a magnetic field. So this is how we can see that, see when the time t is equal to capital T, then there is an electric field but there won't be any magnetic field. So once there will be an electric field, once there will be charge values will be 0, but the magnetic field will be present. Again the magnetic field will not be present, then the charge value will be maximum in certain direction, and again the direction will be changing and there will be a electric field and magnetic field again and again. So if you calculate with all the mathematical expression, in case of LC, you get it as charge is equal to Q naught into cos omega t. Q naught is nothing but a maximum charge on the condenser. And we can say that the charge, because it is cos omega t, here simply we can say that the charge on the condenser is oscillating in nature. And when we say that there is a charge in the condenser which is oscillating, then definitely there will be a time period. And that time period is given as t is equal to 2 pi by omega, where omega is equal to 1 by under root of LC. So this is how we get the frequency value. F is equal to 1 upon under root of LC. Sorry, that was omega is equal to 1 upon under root of LC, and F is equal to, as it is a reciprocal of t, and t is equal to 2 pi by omega, so we can have the frequency as in F is equal to 1 upon 2 pi into under root of 1 by LC. Let's have a demonstration, mass on spring. We will see how the LC works with respect to simple harmonic motion. So let us see this mass on string. Here, if you observe, this mass is attached to a spring where the velocity is 0. So this position we can say that it's an inertial position. If at all, by an external force, on applying an external force, this mass is moving towards this particular body, then we say that earlier it was velocity was 0, here the velocity is maximum. So this was the inertial position, and this we can say it is in a motion. So it is moving towards this particular end, and here again we see that after the spring is contracted to the maximum extent, then the body will not further move. So here again we can say that the velocity is 0. And when we release this particular body freely, then obviously it will come, the spring will come to its original shape and size, and then with a maximum velocity in a reverse direction. So here we say that V is equal to 0, here we say that V is equal to maximum, in the left direction, again v is equal to 0, and here the v is equal to maximum in a right direction, in an opposite direction, we can say that. So we can say that the body was in motion. This is in inertia position. It's nothing but the tendency to move its state of rest can be called as an inertia. And this here we can say that after applying an external force, this body is in motion, isn't it? So when the body is in motion, to make the body into the motion, the force should be applied, isn't it? Unless and until the force is applied, the body will not change its state of rest. So when the force is applied, it means there will be an acceleration. There will be an acceleration. So mass into acceleration is nothing but force. And here you can see that F is equal to ma, or F is written as minus k into x. What is k? K is a restoring force. So once I apply the force and it have come to this particular extent, when I release the force, it is again coming back to its original position. So this is because of the restoring force on this particular mass m, on this particular body which is having a mass of m. So this is called, as it is into the reverse direction, we can say it as a minus k. So F is equal to minus k is nothing but ma is equal to m into what is acceleration? The rate of change of velocity. So d square x by dt square, as the displacement we have taken as an x. So we can simply from this equation m d square x by dt square plus kx is equal to 0. And as it is to and fro from its mean position, it means the body is possessing simple harmonic motion. So before we understand how the LC will work as a simple harmonic nature, we have taken a mass in a linear motion, and we are understanding or making you understanding what is a simple harmonic motion. Whenever a body is flowing to and fro from its mean position periodically, then we say that its body is possessing simple harmonic motion. So when the body is into simple harmonic motion, what is the displacement given? Displacement should be equal to x should be equal to x naught cos omega t plus phi. What is x naught? It is nothing but an amplitude, maximum displacement traveled by a particle. So x will be equal to x naught cos omega t plus phi, where omega is a angular velocity and phi is a phase difference. So angular velocity we can write as under root of k by m, which we say that it is k is nothing but restoring force by mass. So we just have taken a graph, graphically representation of all the terms involved into a displacement equation. So here we can see that this is the maximum displacement. It's nothing but an amplitude. If we say that this is with respect to t and this is x, so x versus t, so this is x naught as a maximum displacement, okay, and time taken for one complete cycle. So half negative will give complete one negative. This is one complete positive. So from here to here, whatever the time it have taken to travel, so this is called as a time period. So time taken for one complete oscillation is time period, which is also a reciprocal of frequency. So what is frequency? Frequency is this number of oscillations per second is called frequency. So we have with respect to frequency and time period formula, T is equal to 2 pi by omega. And equation it comes like here, from here it has started. If the particle is starting from its mean position, then x should be equal to x naught into sine omega t plus or minus of phi. If the particle is starting from its extreme position, this and this 2 points can be called as an extreme, and this is the mean position. So if the particle is started from its extreme position, then we have to take as an x is equal to x naught cos omega t plus phi, where phase shift is phi, which is of the angle of minus phi by 2. The same thing we have taken spring mass here according to the energy. You can take it into 4 categorization. When the velocity is 0, when the velocity is maximum, and again velocity is 0 and velocity is maximum in an opposite direction. So as we have seen the equation as an x is equal to x naught cos omega t plus phi. If you derivate this dx by dt, you'll get it as minus cos derivative is minus sign. So minus omega t, omega naught into x naught into sine of omega t plus phi. So here energy has two parts. What is that? Mass, which is a kinetic, and spring, which is a potential. So energy, total energy is nothing but sum of kinetic energy and potential energy. What is kinetic energy again? Kinetic energy is by virtue of its motion, whereas potential energy is by virtue of its position, isn't it? So that's the reason here the position of the spring, this will give the status of the potential energy, and because the mass is in motion, here we can see that this is in motion, so this two mass will represent the kinetic energy. So these two are nothing but a potential energy, and these two are nothing but a kinetic energy. So what is kinetic energy? It is nothing but half mv square. What is v? V is velocity. Velocity is again what? The rate of change of displacement. So it means dx by dt is v. So we can write k is equal to half of m into v square. So v square is dx by dt whole square. And we just substituted dx by dt. Because we have derivated this, we got this equation. So just square root this, you'll get it as in half k into x naught square into sine square omega t plus phi. Similarly, if you see the potential energy with respect to spring, it can be written as half into k, restoring force k x square. And if you substitute the value of that, so you'll get it as us is equal to half into k x naught square into cos square omega t plus phi. It means energy sloshes back and forth. Now the same spring mass simple harmonic fundamental, we will try to understand the same into a LC oscillations, which is a simple harmonic oscillation. Now what we will do, we have taken this circuit, set up the circuit above with a capacitor, inductor, resistor and a battery. So what we will do is, we will allow the condenser, see if you observe here, this is an open terminal. So through this particular open terminal, there won't be any current in the circuit, isn't it? So if I switch on, if I close this particular switch as, there will be a current in the circuit through the condenser. And after attaining to the maximum charge value of condenser, what we will do is, we will open this particular switch as to this point, and we will connect A point to B point. It means we will allow the condenser to discharge through the inductance value. Hope you are clear. So we are allowing the condenser to discharge through the inductance in the circuit. So what will happen? Let us understand. It undergoes simple harmonic motion just like a mass on a spring, with trade-off between charge and capacitor and current in conductor. Like charge on capacitor is spring and current in conductor is mass. Equivalently, trade-off between energy stored in electric field and energy stored in magnetic field. So this is how it is happening. So if you see that here for each of the circuit, initially what is happening when V is equal to 0, here you can see that the energy stored in an electric field, and again when it has moved, the energy stored in a magnetic field. Here again when it has come to a constant point, stable point, then we can say that here the energy stored in electric field. Again here we can see that the energy stored in magnetic field. So this, we can say that the LC is in oscillations. And how the equations comes? Equation come like the charge in the condenser will be Q will be equal to Q naught into cos omega t plus phi. Here you can see that the total charge will be Q naught cos omega t plus phi. Angular frequency will be equal to omega naught 1 by under root of LC. Amplitude of the charge oscillations is Q naught, and the phase time you will get it as phi. So here you can see the energy, or the in terms of oscillations, you can find it out as in electric field energy and the magnetic field energy. So here you know the electric field energy is equal to, you have the half q square by c, and you have the value with respect to the last equation q as q naught cos omega t plus phi. So if you substitute this, you'll get it as electric field energy should be equal to q naught square by 2c into cos square omega t. Similarly, if you find out the magnetic field energy, so this is given with respect to inductance, this is with respect to charge, and this is with respect to inductance. This is half Li square. So half Li square is nothing but half into L into what is I? I is nothing but I square, I naught into sine omega t. The current in the circuit will be equal to I naught into sine omega t. So substituting that and just rearranging, so UB is equal to Q naught square by 2C into sine square omega naught C. So if you sum up the total energy UE plus UB, it means energy electric field and energy magnetic field, is nothing but, if you add up these two, you'll get it as Q naught square by 2C. It means energy is conserved. So summarizing this, you can see complete how and how much the energy will be there, when and what energy will be working, like magnetic field or electric field. So you can see here both are equal, and then there will be energy because of the magnetic field. Here they are equal, electric field again equal, magnetic field equal, and electric field and equal. So this is how we can say that the LC oscillation happens. Now let us have an example where which the inductance, capacitance and resistance, all the three components connected to each other. Earlier we just took the combinations as an LR or RC or CR and so forth. But now here we took all the three components, L, C and R. One's connected in series, the other is connected in parallel, and understand what will be the charge on the conductor. So consider a circuit having a capacitor of condenser C. Here we can see that an inductance coil L and self-inductance R are connected in series with the source. So after attaining to maximum charge, we are all talking about. So consider the circuit shown. Assume that at time t is equal to 0, the inductor has an initial current value of I naught and the capacitor has initial voltage as in V naught. So after attaining to the maximum charge value, we will be having the maximum current as an I naught and the maximum voltage in the circuit will be V naught. As the time passes, the initial energy in the capacitor and the inductor will dissipate as current flows through the resistor. This results the changing in current which we wish to calculate. So if you apply the Kirchhoff's law, you'll get it as a standard trick for such will get as an Ri plus L di by dt plus 1 by C and limits of integration is minus infinity to t of I tau is equal to 0. So this is a standard trick for such integral differential equation is to take the derivative of both the sides. If you take the derivative, so here, I'm sorry, here it's not displayed. This is R di by dt will be coming as R di by dt plus L d square I by dt square plus 1 by C into I is equal to 0. And if you rearrange that and divide by L, so we can write it as, if you are dividing by L, it can be written as d square I by dt square plus R by L into di by dt plus 1 by LC into I is equal to 0. So here you got it, this is equal to 0 is a second order linear differential equation with a constant coefficient. So once we get it a constant coefficient value, we can have the value of I as well as we can have the value of Q in the circuit. So to solve this d square I by dt square plus r by L di by dt plus 1 by L c into I is equal to 0, first assume that the solution is of the form of I is equal to A into e to the power of st. Where A and S are the constants to be found. So once we get the value of A and S and substitute into this particular equation, we will get the current in the circuit. The steps are like plugging into this equation yields like A square into exponential of st plus r by L into A into S into exponential of st plus 1 by LC into A into exponential of st is equal to 0. So if you take common as A into e to the power of st, you'll get it as square plus r by ls plus 1 by LC is equal to 0. So solving this differential equation, as A into exponential of e to the power of st, A into e to the power of st cannot be equal to 0. This term s square plus r by ls plus 1 by lc is equal to 0. This is called the characteristics equation of our original differential equation, and it is a purely algebraic with one variable s. It has no derivatives, no integrals, no exponential. So to solve this now, you can use the quadratic equation. And for convenience, let us assume the values of alpha as an r by 2l and omega as an 1 by lc. We call alpha the Neper frequency and we call omega naught as an undamped natural frequency. So we can write as an s square plus r by ls plus 1 by lc is equal to 0 as s square plus 2 alpha s, because we have taken as an r by 2 l is equal to alpha. So 2 alpha s plus omega naught square is equal to 0. Now use the quadratic formula, like minus b plus minus under root of b square minus 4ac divided by 2a. If you substitute that, so you get a two solutions which we call it as a natural frequencies. So s1 is equal to minus alpha plus under root of alpha square minus omega naught square, and s2 is equal to minus alpha minus of under root of alpha square minus omega naught square. Because of the square root, we must distinguish three cases. We'll have three cases. When alpha is greater than omega naught, called the overdamped case. When alpha is equal to omega naught, called the critical damping case. And when alpha is less than omega naught, called the underdamped case. So this is overdamped when alpha is greater than omega naught. So our two solutions for S are in distinct negative real numbers. So we will get as S1 is equal to minus alpha plus under root of alpha square minus omega naught square, and S2 is equal to minus alpha minus under root of alpha square minus omega naught square. In this case, the solution to our differential equation is I will be equal to I1 plus, because two negative real numbers we got it. So I should be equal to I1 A1 into exponential of S1t plus A2 into exponential of S2t. The initial condition determine A1 and A2. If you apply the boundary conditions, then you'll have the values as A1 plus A2 is equal to I, and if you substitute the same, you'll get it as S1 A1 plus S2 A2 is equal to di by dt. So here, the next is the critically damped case where we say that alpha is equal to omega naught. So if alpha is equal to omega naught, our two solutions for S are equal to each other and 2 minus alpha. So this comes like S1 is equal to minus alpha and S2 is also equal to minus alpha. So in this case, the solution to our differential equation I will be equal to what? A2 plus A1 into T into exponential of minus alpha T. And according to the boundary conditions, A2 will be equal to I and A1 will be equal to di by dt plus alpha AT. This is the last one, the underdamped case when alpha is less than omega naught. So in this case, two solutions for S are complex numbers. It's imaginary. So S1 we got it as minus alpha plus alpha square minus omega naught square is equal to minus alpha plus j omega t, where j is nothing but imaginary unit of the value of like j square is equal to minus 1 or j is equal to under root of minus 1 into omega d. What is omega d? Omega d is called as a damped natural frequency, where omega d is equal to under root of omega square minus alpha square. We just rearrange this because this we have taken in a minus term. So if it is multiplied by minus, so it will come as a plus. So similarly, S2 is equal to minus alpha minus under root of alpha square minus omega naught square is equal to minus alpha minus j into omega t. So in this case, the solution to our differential equation will be I will be equal to exponential of minus alpha t into b1 cos omega d t plus b2 sin omega dt. And for the initial conditions we have given for the b1 and b2 as well. This is the graphical representation of all the three conditions. Now let us see if the LCR are connected in parallel. The math for source-free parallel circuit is almost the same as math on the previous slides, except that now the variable in our differential equation is Vt instead of It. We define alpha, the Neper frequency. Same applying, instead of I we have taken for the V here for the parallel RLC combinations. So this comes like d square V by dt square plus 1 by RC into dV by dt plus 1 by CV is equal to 0. So by assuming, because it's a second order differential equation, we can say that V is equal to A into exponential of minuses. And where we say that A and S are the constant by which we need to find out the values. So for convenience again, previously what we did, here we will be taking alpha as in 1 upon 2 RC and omega naught as in 1 by LC. Omega naught, the undamped natural frequency, is same as for the series LCR circuit, but alpha, the Neper frequency, is not. Therefore, just as for the series circuit, S square plus 2 alpha S plus omega naught square is equal to 0. And again for this also we will be having three cases: overdamped, critical damped, and underdamped. So if alpha is greater than omega naught, we will have a S values will be two distinct negative real numbers. Here we have given S1 is equal to minus alpha plus under root of alpha square minus omega naught square. S2 is equal to minus alpha minus of under root of alpha square minus omega naught square. So in this case, the solution to our differential equation we will get it as Vt is equal to A1 into exponential of S1t plus A2 into exponential of S2t. And if you apply the boundary conditions, you'll get it as A1 plus A2 is equal to V and S1 A1 plus S2 A2 is equal to dV by dt. The next is when alpha is equal to omega naught. It is called, the condition is called as in critical damping. So here S will have the two equal values of the values of minus alpha. So S1 is equal to minus alpha as well as S2 is equal to minus alpha. So here, because of these two values, V will be coming as A2 plus A1 into T into exponential of minus alpha. And the initial condition to determine A1 and A2 will be A2 is equal to V and A1 is equal to dV by dt plus alpha A2. And the last is underdamped case where alpha is less than omega naught. So here you will have two solutions for S are complex numbers. So S1 is equal to minus alpha plus under root of alpha square minus omega naught square. In terms of J, it is nothing but minus alpha plus j omega d. Similarly, S2 is equal to minus alpha minus under root of alpha square minus omega naught square is equal to minus alpha minus j omega d. So here j is nothing but an imaginary unit, which is nothing but j square is equal to minus 1 or j is equal to minus under root of minus 1, and omega d is called a damped natural frequency. So omega d is equal to under root of omega naught square minus alpha square. So in this case, the solution to our differential equation will be Bt is equal to exponential of minus alpha t into B1 cos omega dt plus B2 sin omega dt. This is a graphical representation of three of the cases. Details will differ based on initial conditions and element values, but the shapes shown here are typical. Note the oscillations in the underdamped case. So with this, we finished up to all the combinations of RC, LC, LR, LCR in series as well as LCR in parallel regarding the varying currents. So thank you everyone for listening so patiently. Stay safe and stay healthy.